Okay, good evening, ladies and gentlemen. May we have the first slide, please? Not that one. That's yours, Alan, right? Yeah, there should be a slide deck ahead of this one, a little introduction. Well, while we sort that out, let me welcome you once again to the 11th Symposium, International Symposium on Field Monitoring in Geomechanics. And welcome to this, which is the first, the inaugural ISSMGE Dunnicliff Honorary Lecture, which will be given by Alan Marr, who's the CEO of Geocomp Incorporated. Thank you. It's a great privilege to be invited to introduce this lecture. I knew John quite well since I moved from the UK to the US in 1981. I learned a lot from him professionally, and in his later years, we shared some fun times together on his bucket list trips. Now, before Alan speaks, let me just share a few words about John and his career. John was born in England in 1934. He graduated from Oxford University with a bachelor's and master's degrees in engineering, and then from Harvard University with a master's degree in soil mechanics and foundation engineering, and then from MIT, where he completed graduate studies in rock mechanics in 1969. He started his career in private practice as a soil engineer with Binney & Partners in London, and worked in Iraq, where he met a colleague, Malcolm Fletcher, who's here tonight, who's joined us. You can hopefully chat with him later. He worked in Iraq, Malaysia, and Hong Kong before moving to the US in 1968, where he became a partner at Zoino Dunnicliff & Associates, which is now known as GZA, Geo-Environmental, in Boston. That was before becoming an independent geotechnical consultant in 1979. John was well known for his participation in the Central Artery project in Boston, which was a big project that lasted throughout the 1990s. And he often lectured about this experience gained throughout this project. But the list of projects he worked on is much longer and included the list here. Doken Dam in Iraq, where he worked with Malcolm. The Waste Isolation Project at Hanford in Washington State. The Waste Isolation Pilot Plant in Carlsbad, New Mexico. The ill-fated superconducting super collider in Waxahachie, Texas. And in the Kowloon Canton Railway Corporation in Hong Kong. So he had quite an illustrious portfolio of projects under his belt. So, educational courses, short courses. John was responsible for more than 100 continuing education courses and seminars on geotechnical instrumentation and monitoring. The courses were held or sponsored by the Federal Highways Administration in the USA, where John lectured to most of the US state DOTs. Then the first courses, as we know it today, were held in the University of Missouri in USA, then at the University of Wisconsin, and then at the University of Florida. And the venue there was Cocoa Beach. And luckily enough, one evening, we were fortunate to see the launch of the space shuttle, which is the slide you see here. When John moved back to England, the courses moved to Europe, and there were a series of courses in Delft, in the Netherlands, before assisting Paolo Mazzanti in courses in Poppi and Rome in Italy. So, at the urging of many colleagues, in 1983, John started to write a book, Geotechnical Instrumentation for Monitoring Field Performance. It was published by Wiley as a hardback in 1988, and then republished as a softcover in 1993. The book is commonly referred to as the Red Book, and in it, he, with the help of a host of co-authors, who John graciously acknowledges, presented a wealth of information, not only about the instruments, but about the applications for which they were particularly suited, and all of this was weaved around an ethic of systematic planning and preparation. To many of us, it became the Bible, a go-to resource, and ultimately it raised the bar with respect to the way geotechnical and structural monitoring was conducted. To this day, the Red Book still serves as one of the main references in our industry, and it is to be found on the shelves of many instrumentation engineers and practitioners around the world. John was asked after the publication of the Red Book, when are you going to do a second edition? And on reflection, on what would be most topical and beneficial to other practitioners, in 1994, he began writing Geotechnical Instrumentation News, which features articles which appeared in 93 issues of Geotechnical News, which was published by Bitech Publishers from Canada. Over the years, GIN became a forum for articles useful to its readers in engineering practice and quickly became a go-to resource for geoprofessionals. And all of those articles are still available today online, and now GIN has been incorporated into the CGS, Canadian Geotechnical Society. In 1998, John returned to England, the country of his birth, where he continued to practice as an independent consultant. He lived in the Dartmoor National Park in Devon until he passed away on October 25th at the age of 86. So, in closing this short reflection about John, please allow me to now introduce you to his wife and best friend Irene, who traveled here today from Devon to be a part of this event, to be with you. As the saying goes, behind every great man is a great woman, and surely without Irene's love and dedication, John would not have accomplished all that he did. Irene, could you stand? And now, let me introduce the speaker for the first John Dunnicliff Honorary Lecture, Alan Marr. Alan founded and leads Geocomp, which is one of the leading providers in the USA in real-time web-based monitoring of civil engineering projects. He's an elected member of the US National Academy of Engineers and was recently awarded the ASCE Seed Medal for his contributions in geotechnical engineering. Alan also serves on the International Advisory Committee for the Center of Smart Infrastructure and Construction at Cambridge University, and he chairs the US National Research Council Committee on Geologic and Geotechnical Engineering. Alan, welcome. Thank you. Over to you.
Thank you, Tony. I told him to keep it really short, and you actually did it. That's great. I appreciate it. And the friendship, Tony. Tony and I have been friends for a long time. As I'd like to consider myself a friend of John's. He was an amazing man. How you tolerated some of him for so many years is amazing to me, but he always ended up with a smile on his face whenever we were together. I taught with him in a couple of those courses in Florida, and Tony was usually there. We would end up some of the nights at a place with lots of beer and crab, if I remember right, and he would egg us into a contest of who could eat the most crab. I can't remember who won. I think I did once. So those are fun times, and I miss them, and I miss him. I want to thank the organizers for inviting me to give this lecture to honor my colleague, my friend, John. It's really a true honor to do that and to be here in this hallowed place of geotechnical engineering. As I was a graduate student at MIT, this was like the other place across the ocean where lots of great things happened in geotechnical engineering. And so it's kind of like Imperial College and Cambridge University on one side and MIT and Harvard on the other side in those days. And it was a wonderful time. I was very fortunate to be young and studying this field when I did. I took on the topic today to talk about challenges and opportunities in geotechnical performance monitoring as I see it today. I thought it'd be appropriate because John was one to kind of talk about what do we need to do better and what might be coming. Some see him, like the book, was a little traditional, never got into electronics, never got into analog digital stuff. But he was very much interested in a promoter of those. And every one of the courses or short courses we did, he brought in people who knew those fields and gave them a forum to talk about them. So I hope I can do him honor with the presentation that I've chosen, or the subject matter I've chosen. I'm going to give you a few memories of a couple of things I learned from John, and then we'll talk about, John always said, what is the question? If you got an instrument, what is the question? And it kind of evolved into my thinking about it as, where is the risk and how can we use monitoring to help manage risk? And John liked that idea. He really promoted and pushed me to continue to do that. So we'll talk about that a little bit. I want to do skip the next section. I took it out to save some time. Some brief cases to illustrate some of the key points I want to make. Some key components, as I see it, to do successful monitoring. Many monitoring programs don't work, and I want to give some pointers as to how to avoid those failures. I want to talk about some challenges that we face today, and one of those being, how do we grow this market? You see a lot of vendors out there and a lot of people competing for the same dollars. One way to do it is to compete and knock somebody out. The other is to grow the market. I want to talk about that a little bit. I want a little bit of a direction on delivering new technologies and a caution there. I want to talk about the word champions and how important that is to monitoring, and I'll close out. First, to deal with John a little bit, and let me make sure I got to make sure I get a timer going here so I can keep control of things. There we go. I think one of the best things I found was recognition of John by the U.S. civil engineering profession. This is coming from ISSMGE. It's really the highest portion of civil engineering society in the United States. And they chose John as a distinguished member for ISSMGE with the citation for preeminent leadership in the field of geotechnical instrumentation and monitoring, and for his long and distinguished career as a specialty consultant dedicated to the improvement of geotechnical practice. Those are pretty glowing terms, and John deserved every one of them. It elaborated a little bit more for his contributions to education about instrumenting and monitoring through teaching more than 100 continuing education courses and authoring 3 books, including the famous Red Book that Tony just showed us and talked about. In fact, I taught, another book that he did was an instruction manual on field instrumentation for the Federal Highway Administration, and I had the privilege of teaching from that book for about 10 years to various state highway departments. From my association interaction with John, mostly in these short courses, I picked up some pointers that I think are very relevant, and I thought I'd start with passing those along to you. You know, the key, all of you who knew John, was said, you know, you got to define what is the question you're faced with that you're considering instrumentation for. What are the questions that need to be answered? And he ended, you'd always say, if there's no question, there's no need for instrumentation. Well, that sounds pretty simple, right? And it really is one thing to start with. Then he said every instrument should have a clearly defined purpose. And he was rather systematic in how he did it. So he suggested you make a table and list the instruments, give them a name, and why were they there? Why is that important? Because many of our projects last 10, 20, 30, 50 years. You get down the road, an instrument dies, do we need to replace it? Well, what was its original purpose? And many times that's lost. Following John's guidance, that would have been captured and we would know and have the background to be able to decide, do we need to replace it? He talked about a systematic approach that Tony alluded to, and he had 17 steps, which grew to 19 steps, I believe it was, of a systematic approach. And he taught around those steps. And I think there's tremendous lessons in those. He did publish those in a paper for those of you who might want to look it up in an earlier time on FMGM. And then he made the point that the people having the greatest interest in the answers to these questions should have a significant involvement in the monitoring. And I think that's really important to us today. Monitoring is divided up in so many ways. There's the original designer, and then there's the instrumentation subcontractor, and then there's somebody who gets the data, and then there's somebody who decides what to do, and then there's someone who takes action, and they don't necessarily get integrated very well. John recognized the importance of making sure that people who really had a vested interest was involved in those steps. And he also was very emphatic that geotechnical instrumentation and monitoring should be procured as a professional services contract with qualified entities rather than going to the lowest bid construction item. And I strongly support that, and we've heard a couple of comments on that here at this conference. There's a great paper on why it should be this way. I remind you of Dunnicliff and Powderham in 2001, and the words there are even more true today. I think we have gone further into the low bid world and away from professional services, unfortunately. So John talked about having a question. So what are the questions? What are some examples of the kinds of questions that John was talking of that we might ask ourselves? Is the facility performing as expected? You know, is it settling more? Is it shifting more than the designers anticipated? Are the conditions that we personally see safe conditions? Is a chance it's going to fall and hurt somebody? Is an emergency condition developing? I won't read all of these. I'll just give you some sense of there are questions out there about many of our facilities that instrumentation and monitoring can help us gather data to give learned answers to these questions. And then getting down to the bottom here, you know, what actions can or should be taken to preserve or restore the safety of the facility? This is so important. I see so many times in projects, I get involved in projects that are in trouble trying to develop workouts, and people just rush to a decision, you know, put a Band-Aid on it. Well, how do you know that's going to solve the problem? Yeah, and with an instrument, we can start getting more to the heart of what is the cause of the problem and devise the most appropriate fix. Instrumentation is really valuable there. And what remedial actions that we're considering might be the most effective from a performance standpoint, not just the lowest cost. So I want to shift from that to, as I listened to John talk about questions, you know, there was, and I don't mean to be negative at all here about him, I learned a lot from him, but that approach does raise some issues with owners. Now, what do you mean? I've hired you, I'm paying you a lot of money to come in here and say, what questions do we need to be answered? And it doesn't always resonate well, particularly with designers. And so he and I talked, and we kind of got along to the idea, you know, what we're really talking about here is risks. You know, that we're trying to help gather data to help manage risks. You think about instrumentation and monitoring, almost everything we do ultimately is aimed at minimizing, avoiding disastrous risks. And so just to remind us, what am I talking about? Risks are about unknowns and uncertainties. We in geotechnical engineering certainly know a little bit about unknowns and uncertainties, I think, right? We're taught that from the beginning. We have so much trouble characterizing soil and defining it with fixed numbers. And even when we've done a thorough site investigation and a fairly advanced analysis, we go to a design, go into construction, we still have a lot of uncertainty. Instrumentation starts to reveal the truth. It starts to show to us how is the site really going to perform. And so I studied for a while and investigated for a while uncertainties and unknowns. What do we really mean by that? There are different characterizations of these things, which I've kind of laid out on this slide. I don't want to go through all these, but we had a famous Secretary of Defense, Donald Rumsfeld, who talked about the known knowns, the known unknowns, and the unknown unknowns. And the academics got had a lot of laughter about all of that, but he was right in ways. And it's useful to think of him that way. And I think there's some more to add to his list, actually, something I call in geotechnical engineering the missed knowns. What is known out there, but we missed it. We missed it in the site investigation, or we just overlooked it. errors and omissions, one of the biggest problems on construction sites these days that lead to big cost overruns and insurance claims. And there's another one I call unknown knowns. You know, that's what others know, but we fail to acknowledge or take into account, something called effective judgment. So yeah, just think about that. There's a hell of a lot of unknowns in much of the work that we do, and much of the work we do is focused on trying to remove or reduce those unknowns to a manageable quantity. But we can't always do it. We can't spend enough money. We don't have enough time to remove all these unknowns. It's kind of like we don't have enough time to answer all of John's questions. Performance measurements can help us. We don't have to reveal all those unknowns. We just have to see what is the performance. And we could get performance, we can measure performance and not necessarily know what caused it, but it's enough to help us know whether we need to stop or go ahead. So I think measurements, performance measurements, provides us with a huge bridge across the large quantity of unknown information that we have to deal with. And I cite that a little bit with an example here from my probability friends. It supports my hand sketch on a Saturday afternoon. Dixie will laugh at me, sees me doing this. But it's a probability of occurrence of particular performance. Just think of the x-axis as like deformation. How much is the building going to settle? Ahead of time, we don't know. And there's uncertainties. We're trying to make a prediction. And our prediction might be a distribution, really, of reflecting our uncertainty. It might be 1 inch, it might be 3 inches, it might be 6 inches, it might be 10 inches. We don't know. But we have some idea that the expected value might be at the peak of this distribution here. And then those of us in measurements start to say, okay, that's kind of what I know, this is kind of what I expect to get, so we'll set a threshold value that if my measurement is above this, I'll start getting a little worried, and then if it gets above the limit value, I'll stop work. It's an interesting way to think about it, because what those values really are reflecting is the degree of uncertainty we have in our predictions of expected performance. And so we're up, at the time we're going to design, we're starting to build, we're really dealing with this probabilistic distribution of the expected performance. The reality is, when we get a measurement, it tells us exactly where we're at. It removes those uncertainties. That is really helpful, really insightful to think that the power of performance measurement is to really open up the uncertain world into certainty on a specific thing. I think that's a kind of an important insight to think about and help us talk about value of performance monitoring. Now, I always look for examples, proof points, and I was reading one of my colleagues' Terzaghi lectures, Bob Whitman, great man, very smart man, and one of the things he had done, we were working on some dam issues and the probability of failure of dams. And so I'm sorry you can't read this event tree, it's tiny. What's in the high text is what I mean for you to see. But what he did is work out an event tree which included branches of it for instrumentation and monitoring. So if the dam starts to fail, does the instrumentation monitoring program indicate it, pick it up in time for us to do something about it? And so this is all worked out in this event tree to say that in a modern earth dam, the chances of a dam failing by cracking, where you have an instrumentation program in place, is about 1 in 20,000 on an annual basis. It's low. Very few dams fail this way. But it gave me a great example, because I said, oh, suppose there wasn't an instrumentation and monitoring program. All I got to do is kill out those probabilities in this from, it's not my judgment, it's Bob's judgment. And without that I&M program, the probability of that dam failing in any 1 year from cracking goes to 1 in 500. That's pretty amazing. That tells us that instrumentation and monitoring properly done for this particular problem, cracking of a dam, has helped or can help us reduce the chance of the dam failing by 40-fold, by 40 times. That's a very important factor. I was on a chase here to try to find out some metrics to tell me how effective is monitoring at helping us reduce probability of failure. This was one really good independent data point. I had a friend who also had a friend at the Panama Canal, which you know, many of you know, suffered from many landslides for many years in the banks of it. And so they had a very insightful engineer, Mr. Alfaro, who had been collecting statistics, and based on frequency of occurrence, he had concluded and wrote an internal memorandum some years ago that their performance monitoring program for landslide control on the Panama Canal had helped them reduce failures by roughly 1 order of magnitude. I got a second data point now on the benefits of effective performance monitoring. And he went on to say that with additional measures that they had in place, he felt they were going to be able to reduce that by another order of magnitude. So 10 to 100 times reduction in risks possible through the implementation of monitoring programs. I'll go one more example of some data on the Boston Big Dig, which Tony mentioned and John had worked on. John wrote the essence, the heart of the technical specifications for this major infrastructure project in Boston. It ultimately cost about $15 billion. My company bid on and won the instrumentation monitoring contract for this particular project, which at the time was the largest monitoring contract that I knew of in the world. The contractors put in the instruments, but then we took over and took the readings and dealt with the reports and answering questions and stuff. And it was in a very dense urban area. Here's an excavation that's roughly 33 meters deep, if I remember right, quite deep. And right next to it are all these high-rise buildings. And so major work there. They developed a very simple monitoring program. There's 7 miles of slurry walls for excavation support system on this project. And so very simple, if the walls move inward 3/4 of an inch, that's yellow. And if they move in 1.5 inch, that's red, stop work. And it was very rigorously enforced. It was throughout that 7 miles of construction. There were 2 problems. One, a concern about deformations, and the other was concern about vibrations. People are very sensitive to vibrations from the construction work. And in Boston, we have many lawyers, so every building owner has a lawyer, and that creates problems. So one of the biggest parts of the monitoring program was actually the vibration monitoring activities. And this is a diagram that illustrates in a common form of peak particle velocity on the y-axis and frequency of vibration on the x-axis. And the solid black line indicates the criterion being used on the project, which came from some old US Bureau of Reclamation, I believe it was, that did this. And so here are measurements over and over again of the peak particle velocity in buildings and the entranceways of buildings. Despite this being well below the allowable for the project, we had complaints every day, frequently. And so the instrumentation program was really vital. Just this simple measurement was really vital to helping us being able to keep the construction going, even though the community was complaining. It also told us where to try to do some stuff to lower these even farther to be a good neighbor. But a simple measurement, very valuable to the project. Had we not have managed or controlled this, we could have had extensive delays from community disputes and lawsuits. Fortunately, we didn't. I went back on the project when we finished after about 8 years, and I'd done some work in risk analysis. And this is admittedly a backward look. It's subjective. It's probably got some bias in it, but it is an attempt to capture some data on what was the value of the I&M program to this project. When I did this, I then went to the project management team, some of the senior managers, and I said, does this make sense to you? And again, it's very subjective, but they agreed that it made sense. So there's some basis for it being legitimate. And we looked at what are some of the significant risks that would have resulted or could have resulted had we not have done this careful monitoring. One was the possibility of collapses. We had several major buildings right within the construction zone of these deep excavations. They could literally have collapsed and fallen in the excavation had we not have been carefully monitoring and controlling all that. So there was an estimate of potential damage of as much as consequence of as much as $5 billion. There were 10 buildings, I think. We estimated each one of those was about 0.3%. So you multiply those two together, which like an insurance company would do, you get some estimate of what the possible risk cost from that failure mode might be. And then major damage and disruption to buildings, cracking, stuff you have to do major rework, same kind of calculation, potentially risk cost of that, about $200 million over the project. Construction delays from unexpected performance. This was a long linear project where a delay here could impact you down here and have enormous cost consequences. That one we actually felt a little more comfortable. We had numbers on to help us estimate that kind of potential loss. And then architectural and structural damage to buildings just from cracks and nuisance kinds of stuff, also being a pretty significant contributor to potential risk costs. So that all adds up to like $550 million, pretty serious money. How much do we actually pay due to these kinds of losses on the project? We paid $9 million to fix one building that had a pretty politically connected guy and had a threshold to his famous building cracked, and so it took a lot to fix it. So we had a potential risk loss of 550. We only paid out 9. We paid 60 for the monitoring program. So looking at it simplistically, this approach, which was a very aggressive monitoring approach at its time in the 90s, but saved the project $500 million in risk costs. That's pretty darn convincing of value returned from a monitoring program. Keep in mind that word value. As the rest of my presentation, you're going to hear that word over and over again. What is the value that we are bringing to projects and to owners? So effective performance monitoring, I've shown you, can reduce geotechnical risk by 1 or 2 orders of magnitude, and it can be very cost effective if it's carried out right. I would emphasize this word I put in here called effective. Just putting an instrument in the ground doesn't change anything. You got to do the systematic approach that John talked about. So let me show you a few examples to illustrate these points a little bit. Here's a bridge we did some years ago in Washington, D.C. called the Woodrow Wilson Bridge. It had to be raised but it couldn't be raised enough to get ships through, so it still is the only lift bridge, or what do you call it, things that go up on I-95, a major north-south road in the U.S. In order to do this, the approach embankments used MSE walls, very high, 60 feet high MSE walls on very soft soils in a very crowded work setting. These approach embankments lead up to the active bridge that's being built, as shown in this picture. If these fail, if something goes wrong here, we shut down access for all the construction materials, and with a potential loss of time of up to a year. Very, very significant risk being faced here. So this is one of the MSE walls. This is a drill rig next to that MSE wall. Anytime you're in this condition, you see a drill rig, you know there's something wrong. And this is an inclinometer that was sitting there and showing the lateral movement of that MSE wall as it was being constructed. What we were worried about is that MSE wall at the base of the embankment had the highest strength reinforcement made at the time. This is plastic material put in like reinforcing steel to help hold the embankment from squeezing out. And so we had a lot of instruments on that to make sure that material, that man-made material, was serving its purpose. And that was all doing good. It didn't move there. What the problem is we had movement starting occurring down here on this inclinometer, down deeper in the original foundation. This is the kind of stuff John was really good at. Make sure the inclinometer goes deep. And in this case, we had it deep enough. We picked up sliding occurring down along an old ancient slip plane in this over-consolidated clay. No one anticipated that. If we had not had this instrument in place, fortunately, this whole thing would have slid. If we'd have kept putting fill on this embankment, it would have slid and we would have lost access and a year of construction time. Huge value from one instrument. And so that's just one example of the kind of value. And it's an example, too, of many times instrumentation reveals unknowns that we didn't think about, we overlooked, or we didn't consider when we were doing design. Here's another example of one of the fewest new hydro plants built in the United States. This is Lowhead Hydro on the Ohio River. It's built in a deep excavation, 100 feet deep, next to an existing Corps of Engineers dam. And the Corps is very finicky about its dams. Thou shalt not move my dam. Thou shalt not hurt my dam. And so we figured a smart way to do this would be a helpful way to do this would be a lot of instrumentation, real-time monitoring. In order to build this, we found, I helped do the engineering on this as well. This lower slide shows the 100-foot deep excavation into rock. That rock had many pre-existing slip planes in it, with the potential that we could get sliding of rock masses along those slip planes. So to prevent that, we put in some of the largest rock anchors ever installed in the United States. I think these are the second largest ones done. They're like 49 strands with 35 kip capacity each, if I remember right. We also had to deal with an existing fault plane that we had identified in the site investigation coming underneath the toe of the Corps of Engineers dam and across our site. So really critical that these rock anchors work, that they take up the load that they need to hold this water force and back and hold this rock in place. And so this example, this plot, I'm sorry the small scale size, but what it shows is readings taken on a new type of instrument that DUIDAG had made that collars around the, one of the anchor strands and gives a measurement of how much force is in that anchor strand. And so we had a design force, that's the purple line here, I mean the blue line we're looking for, and then we had 4 strands in each one of these big rock anchors that we were measuring those forces on. And so how close were we to the design? This one got locked off a little bit below the design load, but that was okay and acceptable. The amazing thing about this is how well this instrument worked and how steady the load was in time on most of these anchors. There was one found in this area where the shear zone, or where this fault zone was, where the red arrow is. It almost immediately, when we excavated this area, it almost immediately showed a drop off in load. It got down to our red line and we really worried, what are we going to do? Now the original plan was, well, we'll just go in and retension it. Like always happens on construction jobs, we forgot the fact is we're excavating all this. We have no way to get back to the tie to retention it. So we had to kind of accept the fact, let's just live with it for a little while and see what goes. It lost a little bit more load and then it leveled out, and we could live with that because the adjacent ties could take, tiebacks could take up those loads. So this is an amazing story of how new technology can come in and help us if we're careful. It doesn't always work so well, and in fact, when these were first put in, they gave us a lot of crappy data. It turned out to be a poor installation, and we cleaned that up, and then you can see what the result was. Another example of a slightly different lesson where this is 2nd Avenue subway in New York. This is a building over here that's about 6 stories tall. It's a little hard to see from the angle of the photograph, but there are many of these up and down 2nd Avenue. 2nd Avenue is a new subway on the east side of Manhattan, and we have to protect these buildings. And most of them are 100 to 150 years old, somewhat sensitive to differential movements, and we're making a new subway out in the street, taking up the whole street and going down as deep as 100 feet. This shows a photo inside of one of those deep excavations for the station portion here at 96th Street Station. The idea of the size and the forces involved given the size of the struts. Here's a set of movements that were taken on that station as we did the excavation, starting from the early days, and the scale down here is every 2 divisions on the x-axis is a month. And the y-axis is 1 inch of settlement, 2 inches of settlement, 3 inches of settlement. So you kind of get a view, and these little marks here are how much different parts of the building settled over time as we went deeper and deeper with the excavation. The excavation level is shown here, and we get down to almost 100 feet deep. You can see the trends with time. We started with limit levels, the yellow limit level, 3/8 of an inch, a centimeter. And the red level was a 1/2 inch. And well, we were the instrumentation contractor, and we were working for the contractor, and I said, this ain't never gonna happen. And he said, well, what do you suggest we do? And he said, well, we have no choice. You bid the job, we gotta do it. We'll do a learn as we go. Kind of sounds like the observational method, doesn't it? We didn't call it that, but the idea was, as soon as we triggered this, we went in and said, hey, look, there's nothing wrong with the building. It's no harm. We can't foresee this building having any serious damage for another 2 inches of settlement or so. So the limits were revised upward. And that's a key message I try to get out to people. Limits they're there to be considered and revised if needed. Many contracts, though, give it, and the contract administrator thinks that's fixed. You're cheating the game if you're trying to move it, trying to change it. We revised the limits on this. I mean, I personally took responsibility for revising the limits on this. I think it was 3 times. And we got down, eventually this building settled a little bit over 3 inches. We're starting to get real worried. You see it took off here as we were getting toward the bottom of the excavation. We went to the sequential part where we just took out a little bit, put in a strut, and watched what happened, poured the bottom, and then moved over. That worked very well, and we were able to succeed. We could not have done it without the instrumentation, though, telling us. We knew we were in a tough spot, but the instrumentation was allowing us to move ahead. So again, specifications should have provisions to adjust these limit values to reflect actual site conditions. Limit values are set up front where you don't know so much. But as you get on the site and you start working, you learn more, you see how the structures are behaving, you ought to be capable or allowed to adjust them to actual site conditions. This is an example of some of the damage that happened to some of those buildings. Joints, we've got cracks here. I think this one is up to 1 inch wide. Got cracks within the buildings. This was someone's bedroom, if I remember right, another bedroom. You know, to lay people, that looks kind of serious, but from a contracting standpoint, this is easy to fix. These aren't structural, they're visual, and so we deal with that a fair amount. As long as we've got instrumentation to help us be sure of how the building is moving and how to interpret these cracks. Don't know what happened here. Somehow I got something in there, but this is go to the next slide. This is a bridge, another example of an old bridge. New bridge has got to be, it's obsolete. New bridge is coming beside it. New piles have to be driven. We're very worried about settling that old bridge and it literally collapsing into the river as we're doing this work. So we put in a monitoring system on that bridge consisting of automated total stations, robotic total stations. And then to be sure that we had it right, we backed that up with some differential GPS just so that we knew that this unit wasn't moving. So this uses satellite data to tell us how much things are moving in XYZ. Amazing device, good to about 1 millimeter and works day and night. So we had good luck there. We got it all in. We had several hundred instruments on this to monitor deformations as well as strains in the structural steel. We're sitting around one day, or people are sitting around, and all of a sudden, the real-time monitoring system sends off emails to multiple people, some who are having lunch, and it says the deformations have exceeded the limits, there's something wrong. What's the first word out of the contractor's mouth? Your instruments ain't working. That's what we always get. So, you know, we send some guy out to see what's the contractor doing, because our answer is always, you're doing something you didn't tell us. So, turns out the contractor had decided to drive a spud pile for getting ready for one of his pile templates for his main 6-foot diameter piles. And it was very close to one of the piers for this old bridge, founded in silts, very sensitive silts. And so that smaller pile driving operation, but a little closer, caused this foundation to settle immediately 1/2 inch. Wow, that was a wake-up call. You know, it said, yes, this foundation is really sensitive, and we better be careful going forward. That in itself was worth an enormous amount of stuff. You know, we got credibility with the contractor that he had to be careful. Fortunately, we were able to use the strains on the structural steel to say no harm had been done. They came in and, again, using our instruments, were able to jack it back to where those stresses were restored, and went on and completed the job without a problem. So, you know, this is an example of unexpected, unanticipated benefits of a good proactive instrumentation program. It tells you the truth, right? And it tells you the basis to argue against the doubters and gives you a basis to how to fix a problem. Another example, and this is where you were using instrumentation in a different way. This is in a design assessment. This is a tailings facility that's been in place for 20 years or more, and there's a concern about the stability. And under new EPA regulations, the owners has to demonstrate that this has a factor of safety of 1.5. for static loading conditions. Now, the engineering practice had been for many years that you would assume that the water conditions were one in which you had the lake level or the reservoir level up at top, and then you would basically lose hydraulic energy in a straight line as you went down along various points in the dam. So we had some drainage ditches here. We knew that that the phreatic surface couldn't get any higher than that. So that kind of establishes what people would call, some engineers would call, a conservative estimate. And then, I'm sorry, this is going to get a little technical, but not for a good geotechnical engineer, but for some other people, like my daughter, that they would assume that pressures are hydrostatic below that phreatic line, right? So that says that, and then we use those pressures along an imaginary failure surface here to calculate what is the safety of this mass. And in this case, what is the factor of safety of this along this sliding mass here? And so if you assume that, as I said, a hydrostatic condition below this line, we went in and put in piezometers, gravity-in-place piezometers, and we measured the actual pore pressures at different points. And this represents how high the water actually was at this point, how high it was at this point. That's way below the phreatic surface from an assumed simple condition. That means the pore pressures along this failure surface are less than half of what that conservative assumption was. And when we take that into account, the factor of safety calculated for this condition went from 1.2 to 1.5. That's huge. The problem just went from a $10 million buttress to fix this project to no cost and much more confidence in what is the actual safety. That's all brought about by good practical use of piezometers. We don't do enough of it in much of engineering. Believe me, this paid for itself many times over. In fact, we wound up redoing the full monitoring system for this client, and they had 10 people working full-time trying to keep up with all their 5,000 instruments. They now do it with a half a person in automation. Those are huge benefits to companies, and we need to try to pull those out. That's huge value generation to a client. I'm going to skip this one in the interest of time, although it's a great story. It's meant to illustrate how on mining with TBMs these days, using instrumentation as feedback to the operator, we're now able to control settlement of the streets to zero. That's really a great step forward. And this was a project in LA where we were able to get to there. By seeing if settlement's occurring, they alter their tail grout operation to make it such that it really is able to keep that street at a constant level. One of the interesting side effects, though, of that is same project is on the stations. These are opened mine stations with retaining walls with cross-lot bracing, or we call them rakers. No, not rakers. It's cross-lot bracing. I'm trying to think of what the British call it, but in this case, you normally expect when you do a deep excavation with a strutted supported excavation that the ground outside is going to settle. Every engineer knows that, right? At least in Boston, that's what we always think. And this case, the engineer had predicted that the elements outside the excavation would settle about an inch. So we've got all these points measuring settlement outside of the excavation, around the excavation, and they're showing data that up at this point is as much as almost a half an inch of heave. So who called me up and said what? Your instruments are wrong. You ain't working. You got them upside down. You got your reference points wrong. Something's wrong. Oh no, we know what we're doing. This is right. No, we don't believe you. So I had to pay for a surveyor to come in and independently check all this stuff. He was right. We were right on the money. We had it right. So everybody's scratching their head. You know, what's going on? And they look to us as the instrumentation contractor. Look, I'm just an instrumentation contractor. I happen to be a geotechnical engineer too, but I was hired there to be an instrumentation contractor. And so nobody can seem to figure this out. So I turned them back. I said, hey, look, this is a deep excavation with a groundwater table. It's a deep excavation 60 feet deep with a groundwater table at 100 feet. You put in one of the stiffest shoring systems I've ever seen anywhere. the lateral movements we've had have been a ½ an inch in a 60-foot deep excavation. And then you went in and you dug this giant hole. What did you do? You unloaded it, right? And you didn't get the normal downward movements that occur because of inward movement of the walls, because they're so damn stiff. You didn't get the downward movement that we normally get from groundwater drawdown to these excavations, because the water's deep. We didn't impact that. You just simply unloaded this. And that was such a insight, I guess, to people. But it shows you conventional wisdom can really take you the wrong way. In this case, instrumentation really showed us. Quite different than what the engineer expected. And it was really, really a very nice experience for us. So let's see. One more I want to show where we I'm just baffled sometimes of where we get caught and instrumentation saves the day. This is a new highway in West Virginia we're working on, and major cuts in highly weathered rock in an area that's known to have a fair number of landslides. A new bridge going across the bottom here. And this area that I've shaded in yellow, with time, we've figured out is moving. It's coming off the mountain. And, but when we first got involved in the project, the bridge pier here was found to be out of position by 12 inches. And the first reaction was, oh, the surveyor got it wrong. We put the pier in the wrong place. It couldn't possibly have moved 12 inches. Let's see, I don't have those. We went out and set up an automated total station. We measured this over a period of 8 months, and sure enough, it was moving. This thing was coming off the mountain at a pretty steady rate. And nobody could figure out, why is that happening? And we were involved doing a site investigation and went and put in piezometers. I always, when you see a slide like this, pore pressures are inevitably involved. I went back and looked at the original contract borings. They didn't show any pore pressure. All the borings were dry. So how could there be pore pressures here? So we put in piezometers. The piezometers not only showed pore pressure, they showed artesian heads in some of the rock. That means water pressures above the groundwater level, ground surface. Artesian heads of as much as 30 feet in part of the rock. And that part of the rock also had a pre-existing slip plane in it from old geologic forces. So here we go from contract borings saying dry holes to piezometers during the actual construction showing artesian heads. That's just total topsy-turvy of what was anticipated. So what's the solution? Put in horizontal drains. Oh, they never work. What do you mean? Oh no, they're always clogging. No, you got to do stuff right. You do stuff right correctly, and you do enough of it, they will work. So we convinced them finally. In fact, I said I'll leave the job. If we don't do horizontal drains, I'm going. We did horizontal drains. Here's just one of the drain pads. I think you see water coming out of those 1.5-inch pipes. In fact, we get about 200 gallons per minute after a rainfall on this mountainside. Huge water pressures building up at times and creating the instability. Once we put those drains in, here is a plot showing the movement of that pier over time. And the scale here is 6 inches of movement. It almost got to 6 inches. Here's where we got the horizontal drains in and working, and the movement stopped. That's a hell of a convincing story. That's a place where we can go back to the owner and say, we have solved this problem. We've got the hard data to prove it. This is not theory, this is reality. And we can go to court and win a court case for a differing site condition, hopefully. Again, instrumentation playing a very key role. I'm going to skip this one. Monitoring delivers value in safety, improving safety, saving time, saving money, and reducing risks. We need to develop and execute our monitoring programs with these objectives in mind. How are we saving money? How can we reduce risk? And then we need to document these, because these are value statements. This is how we help owners to save money, save time. And we don't do enough of this in the monitoring world. We do a great job of putting the instruments in and collecting the data and making nice plots, but we don't translate it into value statements. And I'm going to talk some more about that. Just before I do that, though, as I tried to show in some of these examples, effective monitoring is very important to this. To feed out garbage, we can have the greatest instruments, but feed out garbage, you can't make the kinds of decisions that I gave you some illustrations of with great confidence unless you really believe the data. So key components of monitoring is visual surveillance. And that's just as important as it ever was. It's becoming more of an issue, though, in some ways, or can be, in that we're automating all this stuff and our people aren't in the field anymore. So we don't get that daily feedback on many of these projects. We got to put in the appropriate and reliable instruments in the right places. So many instruments don't go to the right place. They don't think about what is the expected performance mechanism here, and then where do I put the right instrument to detect that particular performance mechanism. Collecting data, you all know about that. Then evaluating and interpreting data, communicating the results and their meaning, and then acting when something is indicated that indicates that something needs to be done, and acting quickly or with the appropriate speed. Again, just to go into these in a little bit of detail, visual surveillance, Ralph Peck said the most valuable instrument we have is the human eye connected to a working brain. And that word working is really important. And he was absolutely right. And as I indicated, automation has kind of taken us out of the field, but there's a new technology development that's bringing us back. And that's these wonderful remote point, tilt, and zoom cameras, video cameras. I'm just now putting a bunch of those on some dams in Puerto Rico. I am amazed at what they're going to do to feed back to a central room and let us look in on a dam after a storm and see, is it overtopped? Is it losing water around the sides? What's happening at the tail downstream end? Just incredible technology. Costs has come way down. We're going to make a big deal out of this. And then drones with a camera and positioning so you know where you're at is also adding a lot of new stuff, capability to us. One of the things on my list was evaluating and interpreting the data. You know, we need to be careful there. There's a difference in evaluating and interpreting, and different people are good at doing these two different tasks. We confuse them a lot. So evaluating means making sure the data are good, making sure they're solid, tight, believable, error-free. You need a team that's doing that, or a dedicated person that's evaluating the data and passing on only good data. Interpreting means what is the implication of all this and what action should we take? Interpreting can be done by somebody who's not really an instrumentation guru. It can be done by the design engineer. It should be done by the design engineer. Evaluating should be done by the monitoring crew. They're the ones that know the instruments. They know what can go wrong. Don't mix those two tasks up. You want data evaluated, clean, reliable, trustworthy, and then you pass it over for someone to interpret it and decide what to do. And I've written on this. I think this is one of the things I see gets mixed up quite a bit. And by the way, I'll share this with, if you guys want. And there's some things I'm not going to cover, but I've listed what are some of the steps one would take in evaluating data and interpreting data. These tasks can take considerable time and well-trained people. You can't short-circuit this on important jobs. Big question is, can artificial intelligence and machine learning technologies help us to do some of this stuff? And the answer is yes, but can they do it with reliability? Can we avoid false alarms? So far, our experience is trying to use these algorithms, they give us too many false alarms and they soon become ignored. But that stuff's getting better all the time. So I think 10 years from now, we'll see a lot more of these technologies used to help us evaluate and interpret data. We'll never take the human being away, but we'll ease up their load a bit. So I also, kind of thinking through all this, thought I'd put together just a few pointers on improving things we could do to improve our monitoring programs. We certainly need to reduce uncertainties in the delivered data, glitches and false alarms. Every place I go that has an automated alarm system, people complain about false alarms. I just been through several major dams, fairly new dams with instrumentation. Half of it isn't working. And why? Well, I don't know, but that's not good. And it doesn't reflect well on our industry. We need to be delivering results in ways that provide value. That word keeps popping up here. That means the data are believable, they can be trusted, they're understandable. that whoever's receiving that data knows what they mean. And in these days of higher technology, I worry about this, that we're delivering stuff that's just hard for others to understand. And in this world, you know, many of our clients are not engineers, and yet they still are responsible for the facility. So we need to work hard to make some of this stuff understandable. And it's got to be put into a form that they know what to do with it. That is actionable data. Just delivering a bunch of volt readings that are all reliable, everyone's there, nothing's missed, but it's voltage doesn't give them any actionable data at all. They don't know what to do with it, and they can't use it right away. So we need to, when we do this and we do it well, we really need to capture, explain, and broadcast in value statements on our monitoring projects so that the word that ends up about the monitoring project is success, benefits, well worth the money, instead of, oh, it quit working, or we don't understand it, or we turned the power off and we didn't really need it, so we never turned the power back on. There's also some things that feed into these things that don't go well. And I just tried to make a list of some of these things that really stand in the way of us doing better I&M projects. And one of the very first ones goes back and violates a rule that John gave us in his systematic approach. Every instrument should have a purpose. That's very simple, very clear, and yet many projects I'm on, I got a list of instruments, no idea what's the purpose of the instrument. That really should be front. In fact, I love to see a table that's the purpose of the instrument, the range, the trigger or limit levels, and then how important it is to the project at what phase of the project. There's a whole bunch here I won't go through in detail. Many of these are obvious to you. John always talks about, you know, or what many of us talk about planning. Plan before you ever go to the job, but then what happens to the plan? Instrumentation crews seem to be made up of a bunch of cowboys. Everyone knows the best way of doing it, and they just go out and do it their way, which usually means it doesn't work the first time. So we have a lot of issues in instrumentation with reworks, and I'm being honest, that's at least with some of our crews. So we just got to up our game and be much more diligent about perfection every step of the way. John used the example of a chain is only as good as its weakest link. And that's very true in instrumentation. It's a lot of pieces that have to work together to get that data from a thing 100 feet in the ground through a thin wire delivered to your phone on the other side of the world. John used to also say, keep it as simple as possible, right? KISS. And to him, that was a very, very simple thing, like a ruler and a pencil. What do you have to say about this guy? That's about the most technologically sophisticated device you can have, yet we all rely on it. It kind of violates the keep it simple, stupid rule, but we rely on it. Let's see. I'll go on from there. We can say all these things and talk about the gadgets. We'll hear a lot of that in the next day or two. We've had a very sobering experience in the last 2 years with the failure of the Brumadinho Dam in Brazil, a tailings dam. And I quote from the expert report done by the Vale expert panel. I'm going to read it. The failure, this was, by the way, most of you have seen it, I'm sure. It killed over 200 people. It was a liquefaction failure, very fast once it got going. The failure is unique in that it occurred with no apparent signs of distress prior to failure. High quality video from a drone flown over Dam 1 only 7 days prior to the failure also showed no signs of distress. The dam was extensively monitored using a combination of survey monuments along the crest of the dam, inclinometers to measure internal deformations, ground-based radar to monitor surface deformations of the face of the dam, and piezometers to measure changes in internal water levels, among other instruments. None of these methods detected any significant deformations or change prior to the failure. That is really a very concerning statement to me. Now, I'm not getting into the details of this. I actually have done some work on this dam. I can't get into the details of it, but I think it's a wake-up call to many of us as we can do better than this, and I know we can do better than this. But this doesn't sound well for our industry. We need to fix this. And we fix it by doing what John told us to do. Systematic approaches, well-designed, well-executed designs, and then getting the data and doing something with them properly. I wanted to talk a little bit about increasing the market for marketing for I&M services, for monitoring services. And I would allege or suggest that we can do that by delivering more value and making clear to our clients and customers that we're doing that and what that value is. We got to demonstrate and communicate value. We can deploy new technologies where they work, or when they work and provide value. By that I mean, don't get out too fast on a new technology. When it's proven that it's going to deliver good results, believable results, and provide value, then we deploy them. And then we can develop broader applications of some of our work. I think there's new things coming that we can do well beyond what we typically think of as geotechnical monitoring. So in terms of delivering value, there's some rules of thumb here. Setting realistic client expectations and delivering on those is just a basic thing. Too many people will oversell and underdeliver. So you got to reverse that. You got to underpromise and overdeliver. I think we should be trying to do a better job of integrating design, construction, and monitoring teams for interpreting data and executing contingency work. So we've heard others talk about the separation. We need to pull people back together. Understanding data and what to do should be a team effort, and it definitely needs to involve the designer who knows the design intent. Skip a couple of things here. Value, I like to get our people to develop value-added statements for every project. So we write a project brief, and the end of the project brief says value statement or value added. And it's really hard to get engineers to do this. They want to talk about, I put in X piezometers and Y inclinometers and they all worked. That's their value statement. That doesn't mean anything to the client, really. The client wants to know the monitoring program saved the project so much money, or it helped avoid a collapse, which if it had happened would have delayed the project X months. The data from the monitoring program helped validate a design change that saved so many months and so many. Those are really meaningful statements. And you can get those. Many of you do this all the time. You just don't take it to the final step of articulating what you really were able to deliver. And I always try, if I don't know, I ask the client. I gave you an example earlier of the tailings dam where we measured pore pressures. We showed the factor of safety was 1.5, and we saved $10 million. I went to the client and asked him, what was the benefit of what we just did? He said, oh, it's $10 million and avoided budgets. That's pretty easy. And now we've done it 15 times on 15 impoundments. That's $150 million. That's pretty serious money. We got it simply by asking. And I urge you to do a similar thing. So we increase market for our monitoring services by delivering value. I think that's a repeat. I went backwards, sorry. So key message, we can improve our future as a monitoring group by creating more value for monitoring services, prove the value generated, and then tell the story. We're all engineers. We're kind of embarrassed. We're kind of shy about bragging. This is not bragging. It's telling the truth. It's really telling people this is a valued service done properly. And then there are various other things that could be done to expand our monitoring market. Again, making every project a success story. We have too many failures in the eyes of the clients. So we need to turn more of those into successes with value generated. I would say we can do some things, and let me illustrate this. Whoops, I took it out. In making monitoring an integrated part of risk management. How many are familiar with risk registers? You know, it's what can go wrong, the probability, the consequence. I think we need to add another column that says risk indicator. What is a sign that that risk is emerging, that something needs to be done? And so that turns out to be really helpful because it brings in the role of monitoring on almost every every significant project that has a risk register. We can do a better job of integrating data and context, and this is just an illustration of where today we're able to bring in not only data, but site information, photographs, almost anything can be put into server farms now and then delivered out to the end user, including to their phones as we show here. There's real value in this because you're communicating information quickly, efficiently, and accurately. And so people can make decisions and move on. I'll skip that. Oh, I did have an example of a risk register in here, but it's so small that I won't bore you with it. But you can see where I'm trying to add in the emerging indicator of risk and how we might monitor it. Many of those for risk management is visual. Another area is future opportunities in monitoring is with existing infrastructure, and it's developing and implementing emergency warning systems and early warning systems. And I'm doing some work on dams right now where this is going to be really important. There's a lot of people moved in downstream of these old dams, and there's not much option to manage risk than to tell people to get out of the way if the dam is failing. And so these are some new, very interesting challenges to be able to do that. Other new types of technology that I think are going to become very interesting, and I wanted to plug here a little bit my friend Kenichi Sojiga at UC Berkeley, formerly of CSIC, on the distributed fiber optic cables and things like drill shafts, where you take the fiber and you circle it up and down this drill shaft 4 times. It's one single fiber going up and down, and it's giving you a strain measurement every meter or so, even a half a meter I think you can do. So they use this in load tests of drill shafts where they were measuring strain with depth for different types of experiments. And just look at the amount of data that's coming out of that shaft where the depth here is 35 feet long. The quality of the data on strain, which we can then use to get load, is amazing. And this was an actually loaded pile loaded through the center. Look at the variability of strain measured in each of these 4 locations through that single fiber cable. Amazing data, amazing information coming to us to tell us about the load lost in that pile along its length due to shaft friction. The whole system can be left in place then and used during service life. So you can see how all this changes. This is the kind of world we're going to be entering in with time if we can deliver high quality data that has trustworthiness to it. And then one other piece is using some INSAR data in ways that you would not have thought of. This is the St. Louis Dam in California we're working on. It's 382 feet high. It's going to be increased in height, but more importantly, strengthened or buttressed against earthquake loading. The material in it is not strong enough to resist an earthquake, so they're going to go into the toe of the dam, widen it out, build a stronger buttress on the outside part of the dam. Now, one of the cardinal rules of the Corps of Engineers and Bureau of Reclamation is thou shalt not excavate on the toe of an active dam. And this dam is got a lot of water in it, and so they're kind of in a bad place. But they're going to proceed with the work. The lake's drawn down 200 feet. And we're beginning an active monitoring program. The concern, though, is if the lake has to go up, what is its effect on our instruments? Our instruments, we want to detect what's the effect of the excavations. But if the lake goes up and it pushes the dam out, then we kind of got a complicated problem trying to interpret it. Somebody got the bright idea of saying, hey, how has the dam moved in the past with changes in the lake? Well, we didn't have any instruments in. How do we know? There's INSAR. And so our good friends at CGG pulled up some INSAR data for us on this dam for the last 4 years and showed that we've had 5 millimeters, an average rate of movement of about 5 millimeters per year over that period of time. And then this is just an example showing how that movement is occurring over those 4 to 5 years of a specific point. So you get a point cloud, but you can pick out specific points. This is points where we're going to be putting in kilometers. So we're going to be able to look backward in time how those points moved, and this is already enough data to tell me we're not going to have to worry about this problem. This is a movement, by the way, that occurred with 180-foot drop in the reservoir level. So the movement's small and very, very valuable and powerful stuff to us. I'm pretty excited what INSAR is going to do for us in looking backwards. How did we get to today? So new technologies will bring great value provided we use them properly, we don't oversell them, and we provide results in understandable and actionable form that can be trusted. One more point, and then I'll just wrap up one slide. Monitoring programs, and this is a new point, I haven't said this before, monitoring programs without a champion mostly fail. What the hell do I mean? I mean somebody who's passionate about the monitoring on the project and willing to go fight for it, willing to keep the budget intact, willing to explain to others why this work is important to the project. Success on a project really requires someone with access to the budget control to explain the purpose and benefits of monitoring on the project and to fight for a reasonable and continued budget. Don't let that budget get knocked down with the same purpose and then says, oh, okay, we'll just cut out some of the instruments. The instruments are there for a good reason if you designed it right, so fight for keeping them there. And this champion can help do that. You need someone to explain purpose and expected benefits of the work and to help keep it focused. The champion can help keep the team aligned and focused properly to deliver good value. Someone to communicate the status and benefits derived from the monitoring program. Someone with a shared commitment to make it a success and demonstrate value. We did a bridge once. It was going to be the first intelligent bridge in Louisiana. We put an amazing set of instruments in the piles. All cast-in-place piles had instruments. They monitored the driving. We then monitored the building of the substructure and the superstructure. I mean, we had this thing nailed. I forget how many data loggers this all came into. It was supposed to feed that data into a fiber optic cable that was to go to the Louisiana Transportation Center. The electrical contractor who was to lay and run the fiber optic went busted on the job and never laid that cable. So we put in a modem, and we paid the bill on the modem until the end of our contract. Our contract ended, the modem got shut off, and the state of Louisiana could not find the money to continue the modem services. Why? The champion for the project had moved on somewhere else, and there was no one to go in to beat on it. We need champions, and projects that are important without them are really a problem. This I've already covered a little bit, expressing value in terms that owners understand, save time, save money. I quoted one of my engineers here as his value statement was, we installed 35 piezometers, 5 inclinometers, and a weather station, all connected to a real-time automated data collection and management system, delivering data to users' phones. That's not a value statement. It's a statement of work, but it says nothing about value delivered to the client. In general, just at the very bottom, performance is statements like performance monitoring saved X amount of time and Y amount of money. Performance monitoring helped us monitor and manage significant risks to the project. Those are value statements. So, closing, last slide. One of the most valuable results of an effective monitoring program is when it reveals unknowns we didn't consider. And it gives us information and time to implement responses immediately to manage safety, risk, time, and money. You know, how many jobs have you been on where something happened and you just never expected it, but the instruments told you, and they gave you time to respond? That happens to me over and over again, and that's immensely valuable. We need to extract value derived on our projects and lessons learned from monitoring, both for successes and failures. And do so as the project progresses. It's too late when you come after the project and try to figure this stuff out. You really need to get in the habit of, hey, we saved the client today. Let's go into the project record and make sure we grab that, because by the time you get to the end of the project, much of that information is lost, gone, and it's hard to retrieve it. We need to quantify value provided by monitoring in terms of improved safety, saved money, reduced time, and managed risk, and then broadcast that out. We can expand the market for monitoring by delivering actionable data that are understandable and believable. And we should be very alert to delivering value in ways that were not envisioned during the planning and stages, and then make sure we call out that benefit and tell the client about it. You know, you do a good deed for a client, if you never tell them, they never know. And so I think we need to do a better job of communicating the results from these splendid monitoring programs you all get involved in. So I went a little bit long, but had a lot to say. So I hope that was useful, and I really appreciate the opportunity.
Well, and on behalf of the organizing committee, I've been instructed to give you this small memento. Thank you very much for the lecture. Everyone enjoyed it, as you could see, and we really appreciate it. Thanks very much.
Thanks very much, Tony. Thanks for your support. We had a debate whether to take questions or not. I know it's late. Nope. Time out? All right. I'll be up here if you want to ask a question.